In this video, Dr. Francis demonstrates how to program a loop in R, particularly in conducting a marker trait analysis. The merged data from the previous video or video part 1 was used in the simulation. The loop was used to automate the ANOVA and summary table generation for the 271 markers.
So what I did in the script is I just simply suggested that you try some other markers. Okay, so you modify those models that we wrote to try some other markers. Okay, so here's a marker. I suggested that you try a different one, and so one way of trying a different one is just copying and pasting it in here. Okay, and then we'll just go ahead and run that. Okay, and so when I look at this, well, that looks interesting. So it's also possibly associated. But let's go ahead and look at that summary. And when I do the summary, I see this kind of uh-oh. I don't have 3 allele classes. So there's something wrong with the segregation of this marker. So I might have to go back in and look at that marker a little more carefully. So why could I get this situation where I have, say, only A and H or only B and H? What would cause that? So I went to this slide here to get you guys to think about how we're actually scoring these, where we sort of create these clusters, right? And so anything that falls out of, say, this cluster could be scored as a heterozygote. It could be just a bad marker. It's a marker that doesn't work very well. Or the primer for this allele just doesn't work at all, so I'm either going to score it here or here. So it's a fishy marker. That's the point. Okay, so I mean I don't want to dwell on it, but the point that I want to leave you with is that there is maybe some data checking that needs to be done. So here's the thing. How many markers do we have? So we have 261 markers. So do we really want to write out 264, it's actually 261 marker trait models? And I think the answer was an overwhelming no. And so what I want to do is I want to introduce you to the concept of a loop in programming. I need to acknowledge some web resources that were developed by Peter Koch at the University of Warwick. I used to give you a URL for his tutorial on loops. Well, it turns out that URL is no longer valid. But I still feel like I need to credit Peter for essentially through an online resource teaching me how to create loops. Okay, so for loops in R, there are 2 basic loop structures. One is a for loop and one is a while loop, and we're going to go over both of those briefly. But the for loop can basically be written as for and then some variable in a sequence and an expression, or we can set up some nested expressions. So this is kind of the generalizable syntax, the grammar of a loop, if you will. To better understand that, let's do something more concrete. What this loop is doing is it's calculating the square root and returning that value for a vector from 1 to 10. Okay, so what I would suggest you do is go ahead and type this into the command line and see what you get. See, I have the advantage of being able to copy that. So the bottom line is that rather than having to do square root 1, square root 2, square root 3, it's just repeating this from 1 to 10. So for x in the vector of 1 to 10, print the square root of x. And so it's going to repeat that 1 to 2 to 3 to 4 to 5 till it reaches 10, and then it's going to stop. Okay? And that same loop can be written 2 different ways. Similarly, the while loop has while, a condition, and then an expression. Okay? And you can set it up with nested expressions as well. Okay? And so the example for that would be to write a loop that produces a specific series. So a Fibonacci series consists of a string where each number is the sum of the previous two numbers. 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, etc. Right? So what we do is we can define our start point as 0, our next point is 1, and then we can say for b is less than 50, print b, okay, temporarily assign, temp is assigned as a plus b, b is then assigned as a, and temp is assigned to b. So we're basically walking it through. We're going to start with 0 and 1, but then we're going to go to 1 and 1, and then 1 and 2, 2 and 3, etc. Right? And so this while statement, or this while loop, will produce a series of numbers. Okay, and then there's modifications, and so this is just another modification of that Fibonacci series. So again, you can try typing these in and see what you get returned. Yeah, so that second while loop appends a new value to the end of this vector x, and you can see what it's doing here. Okay. In this slide, what I'm introducing you to is how to write a function in R. Here what we're doing is this function n, and we're assigning it to Fibonacci, right? And then we define it. Okay, and so the syntax of using that is then you've got this function that you created called Fibonacci, and you could write Fibonacci 10, and it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. We create this, and then we put it into an application here, right? So every time I want to create a Fibonacci series, instead of writing this out, I just write this out once, and then I can do it for 10, for 20, for 30, whatever number I want. So I'd like you to play with these at home a little bit and see if you can understand what you're doing. Instead of the Fibonacci series, you could really do any kind of a mathematical set of equations. I'm going to skip through there, and I'm going to get back to our marker trait models, because this is the meat of what we're trying to do here. Okay, so the marker trait models that I'm going to use are going to use the for loop. For our variable x in column 4 to n column in the file D3. So n col means the last column. Why am I starting with 4? Starting with 4 because that's my first marker. So what I'm doing in this model is, first of all, I'm saying use x from 4 all the way to the end. Print the names, and that's important because if I don't print the names, I have no idea which marker I'm looking at. And then I run the ANOVA, and so I've nested this. So I'm saying print the ANOVA for the linear model, fruit number versus x. And here this bracket comma x means x is a column header, it's not a row header. And so if you run that, what do you get? So I can run it here. So what did it do? It just ran all of those ANOVAs and spit it out because I told it to print it, right? So we've kind of solved the problem. You guys don't have to copy and paste those marker names. So all you have to do now is you just have to go out and search through that output and tell me which ones are significant. Okay, maybe not. Maybe we can do a better job of this. This is how I tend to think about big problems. Identify the limiting step, remove it, reassess the problem. What's your next limiting step? Remove it. The first limiting step was you guys were not wild about this idea of cutting and pasting marker names into a model statement and running that 261 times. Nobody was happy about that. So then we just solved it by we wrote this loop that did that for us automatically. And so what happened? It just spit it all out to the console, and we still have to go through there manually to identify which ones are significant. Okay, that's less than ideal. So let's figure out a way around that. What I'm going to do, my approach to this is going to be to run this loop several times. The first time I run it, I'm going to create a vector which is just the names. And so I'm going to have a vector which has the names of the markers. Then I'm going to do it with the ANOVA. I'm going to pull out the F value. Then I'm going to do it again, and I'm going to pull out the P value. So when I think about what I want, if I want to assess whether markers are significant, I want to know what the F value is, and I want to know what the P value is. With 3 loops, I can create a vector of the marker names, a vector of the F value, and a vector of the P value. Right? And then I can pull those all together and I can write them out. Instead of having this whole console worth of display to go through, I'm going to have a simple file which has 261 rows, one for each marker, and it's going to have an F value and a P value. This is what I end up with. So the first ones, it's null because you don't really do an ANOVA for the genotype. I don't really need those. But then I get, for my markers, I get an F value and a P value. Okay? And I can write that out, and then I've got an easy way of searching for which ones fall below or above a certain cutoff. And so here's an example of that file, and I can kind of search through it, and I can find an example of markers that fall below the 0.05 cutoff and are potentially linked to genes that affect the number of fruit that I get per plant. In some cases, these are these SNPs may actually be in candidate genes for like the branching of the inflorescence.